Right, so welcome back to Advent Code. This is day 18, snailfish. You descend into the ocean trench and encounter some snailfish. They say they saw the sleigh keys. They'll even tell you which direction the keys went if you help one of the smaller snailfish with his math homework. Snailfish numbers aren't like regular numbers. Instead, every snailfish number is a pair. An ordered list of two elements. Each element of the pair can be either a regular number or another pair. Pairs are written as xy, where x and y are the elements within the pair. Here are some example snailfish numbers, one snailfish number per line. This snailfish homework is about addition. To add two snailfish numbers, form a pair from the left and right parameters of the addition operator. For example, 1, 2 plus 3, 4, 5 becomes 1, 2, 3, 4, 5. Okay? There's only one problem. Snailfish numbers must always be reduced. And the process of adding two snailfish numbers can result in snailfish numbers that need to be reduced. To reduce a snailfish number, you must repeatedly do the first action in this list that applies to the snailfish number. If any pair is nested inside four pairs, the leftmost such pair explodes. If any regular number is 10 or greater, the leftmost such regular number splits. Once no action in the above list applies, the snailfish number is reduced. During reduction, at most one action applies, after which the process returns to the top of the list of actions. For example, if split produces a pair that meets the explode criteria, that pair explodes before other splits occur. To explode a pair, the pair's left value is added to the first regular number to the left of the exploding pair, if any, and the pair's right value is added to the first regular number to the right of the exploding pair, if any. Exploding pairs will always consist of two regular numbers. Then the entire exploding pair is replaced with the regular number 0. Here are some examples of a single explode action. So the 9 and the 8, and the 981 bit has turned into 09. I think what's happened is we've lost the 9 because it has no regular number to its left, and the 8 has been added to the 1. Yeah, and the exploding pair has been replaced with 0. Okay. The next example. The outer 765 part remained the same, but 4 followed by 3, 2 turned into 7, 0. The 2 has no regular number to its right, so we lose it, and the 4 and 3 get added together. So in this one, 6, 5, 4, 3, 2, 1. The 3 got added to the 4, the 2 got added to the 1, and the pair got replaced with a 0. Okay, well, let's accept that for the time being. To split a regular number, replace it with a pair. The left element of the pair should be the regular number divided by 2 and rounded down, while the right element of the pair should be the regular number divided by 2 and rounded up. For example, 10 becomes 5, 5, 11 becomes 5, 6, 12 becomes 6, 6, and so on. Okay, that makes sense. Here is the process of finding the reduced result of this addition. Firstly, we form a new pair consisting of the two input pairs, one on each side. And then we do an explode operation, and then we do an explode operation, and then we split and split and explode. And once no more actions apply, the snailfish number that remains is the actual result of the addition operation. The homework assignment involves adding up a list of snailfish numbers. The snailfish numbers are each listed on a separate line. Add the first and second, and then the third, and so on. Yeah. Okay, fine. We only check the magnitude of the final sum. I wonder if all of these operations don't change the magnitude, and then we can just ignore all of the split and explode stuff. The magnitude of a pair is 3 times the magnitude of its left element plus 2 times the magnitude of its right element. No, that doesn't sound like the process maintains the magnitude. For example, the magnitude of 9-1 is 29. Yeah, fine. Magnitude calculations are recursive. It seems like the magnitude of a leaf node. Oh, I see. No, I understand. Okay, fine. More examples. Yeah, fine. Add up all the snailfish numbers from your homework assignment. Just going to do some silent contemplation. I wonder what the identity snailfish number is. So the additive identity. What snailfish number, when added to any other number, doesn't change that number? Don't know, maybe there isn't one. I think I need to read the problem a bit more. If any pair is nested inside 4 pairs, the leftmost such pair explodes. Well, let's start by reading the input. And we're going to do this with a little recursive descent parser. What are we going to call it? So snail will read in a single, okay, we'll call it pair. We'll just call it snail. Snail will read in a single pair. So what we'll do is, okay. When snail gets to the end of the file, we'll return 0. Otherwise, we'll set that the character is and then we'll read the leftmost number. No, we don't set that it's a thingy. If it's a digit, are they always reduced in the input already, or can we have multiple multi-digit input numbers? I think they all look like single-digit numbers. So if it's a digit, then this number is just that digit. And what I'm going to do, which is kind of unpleasant, is a snail a snailfish number will be a bunch of const pairs except the leaf nodes will just be their number, and we'll tell the difference by the size of the number because the pointers will all be much larger than the digits. So if it's a digit, we return it. Otherwise, we assert that the character is an open paren. And the left is a snailfish number. And then we have a comma. And then the right is a snailfish number. And then we have a closed paren. And then we return const left right. And having read one, we'll assume there's a new line. Okay, and now we could have a way to dump a number. So, if S is greater than, let's say that much, then we'll put an open bracket, we'll dump left, we'll put a comma, dump right, and we'll put a closed bracket. Otherwise, it's less than that much, we'll just print its value. And when dump is over, put a new line. So this should just echo the input back out. I wonder if I'm going to need a way to free these snailfish numbers, or if it's fine to just leak all the memory. I think we'll just let it leak all the memory for the time being, and if it runs out of memory, then I'll write a function to free them. The function to free them would look almost exactly like dump, except you replace the word dump with the word free, or the word snail free. Great, that looks like it works. So, since I can't figure out what the identity snailfish number would look like, we'll just initialize S to the first snail, and then we'll set and then we just reduce const S with snail. S2 is a snail, and we'll reduce. No, okay, I know what to do. There's no S2. S is const of S with snail, and then reduce S. Nope, got it wrong again. We do need an S2. Because if not S, we need to break, and then S equals const S of S2. And we no longer dump. And then maybe we'll dump S at the end. But that's not exactly what we want. We want to calculate the answer. So what does the reduction function look like? Well, let's just say Y1 for now, I'm not sure. No, I'm in trouble. So it's explode. If there's no explodes to do, then it's split, I think. Yeah, so the first pair that is nested inside 4 pairs explodes. Greater than or equal to 10, splits. So, actually, I don't understand the explosion thing. The pairs, the leftmost pair that is nested inside 4 pairs. So, let's say something's nested inside 7 pairs. The leftmost pair that is nested inside 4 pairs would be nested inside exactly 4 pairs and would have more pairs inside it. So we want to explode the one that's inside exactly 4, and then in the next loop we'd do another one. So if S isn't a pointer, we're done. Otherwise, if we can explode the left side of S at 3 levels, we continue. If we can explode something on the right side of S at 3 levels, we continue. Otherwise, it's to do a split. And if we reach the end, we'll break. So what does explode do? Explode will return 0 if it's not going to split it. So if it's a leaf node, I don't think we do anything in any circumstance, even if levels is 0. Yeah, so explode is left added to first number left, or discarded if none. Right is added to the first number right, or discarded if none. And then the pair is replaced with a 0. So that makes the recursive function quite annoying to write. Well, the first number to the left of the left number is the very rightmost leaf node of the parent, right? The first number to the left of the left number is the very rightmost leaf node of the parent. So if S is if S is a leaf node, let's see, well, we'll just say no explosion needed. What we'll do is we'll maintain a pointer to the parent node, and then if levels equals 0, then what we'll do is add to the if this is a right child of the parent, then the leftmost number is the rightmost leaf node of the left child of the parent. If it's a left child of the parent, then the rightmost leaf, then the next number left is the rightmost leaf of the right child of the parent's parent. Ugh. So we need to keep track of I wonder if this problem would be easy to solve with regexes. I don't have regexes, but it might be funny. Right, let's see. If we are explode, so if levels is greater than 0, then we'll return explode. Well, I don't know exactly what the arguments will look like. Now, if we get to here, otherwise we actually do the explosion. And return 1 at the end. So, we need to know if we're a left leaf or a right leaf. Oh wait, hang on. If any pair is nested inside 4 pairs, the leftmost such pair explodes. Well, that can itself be a pair. To explode a pair, the pair's left value is added to the first regular number to the left. Oh, well, I don't think it can get any deeper than 4, actually, because each step of addition can only increase the depth by 1. So if we get to the 4th level, it must be a leaf node already. So we'll just have a left and a right tree that we need to add to. If the left, Yeah, so we need a parent as well. So the parent of S0 is S. The left tree that we would need to add to is the parent's right tree. And the right tree that we would need to add to is S's right tree. So if it's a right-hand tree, then the left tree we would need to add to is S0, and the right tree that we would need to add to actually, the location of the left and right tree depends on the route we took to get here, doesn't it? That's really annoying. Well, I'm just going to draw a tree that's 4 levels deep. One, two, three. Well, it sounds like a snailfish number can only ever have at most 8 digits in it. Otherwise it would need to go to more than 8 levels. But this has more than 8 digits in it. Maybe I'm counting the levels differently. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Maybe 16 is the most you can have. Nested inside 4 pairs. Well, that's inside 1 pair, that's inside 2 pairs, that's inside 3 pairs. Okay, so this is inside 4 pairs. So 16 digits is the maximum you can have after it's reduced. So you might need to go all the way back up to the root to add something to your left-hand neighbour or your right-hand neighbour. What is the best way to do that? Maybe my const pairs. Maybe my const pairs aren't powerful enough. Maybe I want a parent pointer on each node as well. But hang on, in the problem statement, this large example, 13531387, is 1 not nested inside 4 pairs. It's inside the pair with 1, 3. That is inside a pair, that is inside a pair, and that is inside a pair. So that one's not reduced. any pair is nested inside 4 pairs. Okay, so we can actually have 32 leaf nodes, but when reduced we can have 16. I wonder why I'm finding this so complicated. The thing that is to the left of a left tree is the thing that was to the left of the parent's left tree as well. The thing that is to the right of the left is the right. So we want S, parent, the thing that's to the left and the thing that's to the right. So we want to add to the leaf node of L, S0, we want to add to the leaf node of R, S1. And is that going to be right? First, we don't have anything parent left. In fact, we don't need a parent pointer because we don't use it anyway. We just need a left and right neighbour pointer. Is that going to be right though? When I explode my leftmost child, the thing that is to the left of my leftmost child is the same thing that is to the left of me. And the thing that is to the right of my leftmost child is my right child. Yeah, that seems believable. So in addition to adding these, the whole pair gets replaced by 0. So the kind of messy, but do we think that's correct? We replace the pair with 0 by writing a 0 into the thing that currently points to this pair. And we'll either comment it out or call the snail 3. Okay, well, that's fine. Now we just need add to leaf. So if S is a leaf node, if S0 is a leaf node, then we'll add it to S0 and return. Otherwise, if S1 is a leaf node, otherwise, if add to leaf S0n, then we return. Otherwise, if S1 is a leaf node, we'll add it to S1, return. Otherwise, we'll return add to leaf S1. Kind of messy and duplicative, but that might be explosion done. So I wonder if it's easy to test explosion. Nine, 8, 1, 2, 3, 4. So let's have part 1. So the left-hand one will be 1, 2, 3, 4, 9, 8, 1, 2, 3. What did I cock up there? We need an open paren and we've got a new line. I don't think we need an open paren, I think that looks right. Oh. Because the initial one doesn't annoying. But we can test it without that. Right. Nine, 8, 1, 2, 3. That's our left one, and then 4 is our right one. And hopefully the result of that is need open paren. A single digit is an allowable snail according to our thing, isn't it? Yeah. What's the problem with that then? Oh, the problem is here I wrote if not S instead of if not S2. So we want to see it reduce that one, which is 1, 2, 3, 4, 5, 9, 8, 1, 2, 3, 4. Which becomes, it should become 0, 9, 2, 3, 4. So what have we missed there? We've replaced the 9 and the 8 with a 0, but we haven't successfully added the 8 to the 1. So we need to add the 8 to the rightmost child of its parent. So why doesn't that work? Well, for starters, we only want to do this if these are defined. I wonder why that didn't work. Yeah, so we're not adding the 8 to the 1. So this is the leftmost pair. So the right-hand tree should be S1, which it looks like it is. But add to leaf isn't working. Oh, we need to know whether we prefer to go to the right side or to the left side. So if we're adding something on the left, we want the rightmost leaf of that left thing. So is that more like it? I still don't think that will work. So if we've got a left tree pointer, we want if L greater than 0x100. If we've got a left tree pointer, we want to add to the rightmost leaf of our left tree, our left value, which seems right. Everywhere I've written less than, I should be writing LT instead of less than. So this, because pointers are unsigned, aren't they? We don't want the entire top half of memory to count as constants, as digits. Yeah, so that still doesn't work. But why? This part is obviously happening because our 9 turns into a 0. I feel like it might be that the 8 is getting added to itself, or something like that. So 9 and 8 are at the deepest level, and the 1 is at the next level up. So when we go down the tree, we say explode S0, which is, so at this point we've got a 1 on the right, and we've got 9 and 8 on the left. So when we go explode 9 and 8, the thing to the left of 9 and 8 is a null pointer. The thing to the right is just a 1. So we need a pointer to the left-hand tree, not Yeah, so the problem is if the other child is a leaf node, then we can't add anything to it. What is the best way to do that? Maybe we will just put a pointer to it. So then this gets given a pointer. I'm confusing myself here. That doesn't want to be value of, that just wants to be if we've got a pointer that's non-zero. What we'll do is we'll just handle that case up here. So if the value of L is less than 0x100, otherwise do this. Seems like it's not the best way to do that. It would have been better to make the add to leaf functions operate on pointers to nodes instead of nodes. But I'm confusing myself with too many levels of pointers. Oh, that looks right. Great. Good, that's explosion done. Now, what was splitting? Well, maybe it's explosion done. It's explosion done for now. Splitting, I think, was easy. Anything that's greater than or equal to 10 gets split to let's make it take a pointer. So this would be s divided by 2 and s minus s divided by 2. So that 11 goes to 5 and 6. And then we return 1, otherwise we return 0. And that's it, I think. So, oh, otherwise we need to recurse, don't we? Still wrong. If it's less than this much, then if that, well, actually, and that should be greater than or equal, so, okay. If it's less than 10, do nothing. Otherwise that. Oh yeah, I don't accept. Annoying. I don't accept multiple digit numbers, do I? Well, let's try and find an example then. I realised another problem as well, which is that reduce needs to take a pointer. Otherwise, if we need to split the top element, Nought 7 4 7 8 6 0 8 1. Was that correct? It is correct. At least the digits are correct. And then what's the how do we calculate the final answer again? Oops. 3 times the left plus 2 times the right recursively. That's going to be... Oh, is it going to be big ints? Let's just say it's unsigned for now. And then snail mail. So we want 3 times the value of the left plus 2 times the value of the right. That looks believable, and if the answer is obviously small or crazy, I get the sense that it might need to be a big int. Maybe I'll just write it as big int in the first place. It's going to take 2 minutes to compile. Might actually be easier. And I think we'll leak big ints just the same way we leak the snails themselves. Oh, I got it wrong anyway. So that will give us a big int for the left, which we want to multiply by 3. And we want to get another one for the right. Which we want to multiply by 2. And then we want to add to B2. If it's a digit, then we make a big int out of it. Otherwise, we work out what the left thing is worth, multiply that by 3, work out what the right thing is worth, multiply that by 2, add them together and return the result. And we're actually not leaking as much as I thought because it's easy enough to free them. So that's the output from the first line. I wonder how long this will take. Maybe I should have put it on a smaller input first. I think I'm going to stop this. So I'm going to make it dump each one as it goes. And it might be that it's taking so long because at some point the explode step is adding a pointer to some other value, which then takes loads of steps of splitting to turn up into something smaller, which then implies loads more steps of exploding. I'm not sure. Was there a full input somewhere? Right, so given this one, 4,140. Oh, hello. Maybe it is correct. Maybe we just need to leave it for a long time. Well, that's an hour and 20 odd minutes in so far, an hour and 26 in now. So I'll just leave it running. Actually, I just want to see how long the input is. Does it take a file name or do I need to put it on standard in? 100, so that's 10 times as long as sample 3. So that was about 45 seconds. So we would expect it to take about 450 seconds, which is about 9 minutes. I wonder why it's so slow. Is it just that this exploding and splitting thing actually ends up resulting in a lot of operations? Or have I implemented it badly? I don't think I've implemented it badly. Oh, I mean, I don't think I've implemented it computationally badly. The crazy stuff about pointers meaning different things in different places is a bit ugly. I wonder if we're supposed to work out some consequence of this exploding and splitting so that we can cut out a load of work and just jump to the end in one step. Anyway, I'm going to leave that for 9 minutes and I'll be back. I wonder if the reason it's so slow is just because we're doing those divide by 2s in the splitting step. So not only are we doing twice as many divides as necessary because we're calling div s2 twice, but it would be better to do a shift right by 1 rather than a divide by 2. Shift right is still expensive on this architecture because the CPU actually doesn't have any hardware to do bit shifting. So it's implemented as test which bits are set and then set the corresponding bits in the output. Oh, so that only took about 6 minutes. So, okay, now let's work out what part 2 is. Oh no. Well, we have O of n squared possibilities for pairs of these snailfish numbers. And since it's already taking 6 minutes, if we were to multiply that by 100, that would take 600 minutes. Well, we're doing 100 additions, we're doing 99 additions currently. If we had to look at every 100 times 99, we'd be doing 100 times as much work. So that would take 10 hours. Problem. Well, let's have a look at the list and see if we can rule any out. The problem is the ones we can rule out are the small ones, which wouldn't take very long anyway. But actually, I don't even know if that's true. Can we rule out the small ones? Like 4, 9 Is it possible that adding 4, 9 to something else produces a larger result than this one? I don't know. And most of them don't look small enough to rule out anyway. I wonder if we just sorted it by line length and added those two together, would that be the correct answer? It's worth a try, isn't it? So the first one looks pretty long. What's that? That doesn't tell us which column we're on. But that's like here. I've got my hand on the screen. So as I go down, if I find a longer one, okay, there are 3 that look like long candidates. So that one's a long one. Oh. Whoops. Okay, yeah, that's the one I was after. So these 3, I think, are plausible candidates. So there are 6 different ways to do that. Well, the middle one, which one do we think looks smaller? This is definitely not going to find the right answer. Let's just delete that one, add those 2 together and see what it does. Too low, okay. What's the plan then? Let's just try those in the other order. Well, it's larger. Too low. Maybe we just do the 10-hour thing and come back to it this evening. Well, we can fix the division, can't we? Where is the division? It's there. I wonder if that will make it substantially faster. It seems unlikely. No, I still think that's not fast enough to be doing 100 times as much work. Well, I guess it's silent contemplation time. The problem is that when you have a number 10 or larger, splitting that number increases the depth of the tree, which then causes you to explode that thing and add those numbers to other numbers, which then, if they're large enough, means they need to be split, which increases the depth of the tree, which means other things need to be added, which means they need to be split, and so on. So I think, really, what the problem is asking is for us to understand what's going on there and implement it more simply. Or maybe it's just asking us to write the quadratic search thing. I wonder if we can easily rule any of the input out. Well, I think what I'm going to do is write the quadratic search thing and then just walk away and leave it for 10 hours or however long. So we probably do want snail free now. And we'll have snail clone as well. And then what we'll need to do is when we read in the input, we'll want a list of snails. What was it? 100 or something? No, equals snail. And then the rest of this, we actually don't need big int stuff, do we? Because the answer was only like 4,000. So snail null doesn't have to be a big int. So having read in our snails, we need to go over every pair of snails. And actually, input reading thing is wrong, because the final snail will be so now we want to clone S well, actually we want to clone snails I and snails J, and reduce that and if snail null, so I wonder if it's possible to calculate the mul without doing all the tree operations, don't know. And then we'll free the snail that we've thus created. Well, good, that's the same answer we were getting before. Yeah, great. And it does them in the other order. And we know it takes about 6 minutes to run all the way through 100 editions. So, yeah, it's going to take a long time. Right, well, I guess that's it for now. I might be back later. See you in a bit. Right, well, what happened is I've actually got the answer now. It took about 40 minutes to calculate, and it got the answer about 40% of the way through the search space. So we can expect it actually we're only going to take an hour and 40 rather than 10 hours, which is good. While it was going, I actually stopped it and made a couple of changes. So I thought since all the numbers we're divided by 2 are really small, I would make a lookup table rather than doing the shift right. So instead of like 32 instructions or however many it is to do the shift right calculations, it's just a table lookup. And at the point I added that, we'd already searched up to about I equals 14. So I also made it take I on the command line. Anyway, yeah, great success. Didn't take as long as I thought it was going to. Good stuff. Thanks for watching. Goodbye.